Okay, welcome back to Unit 3. We're in that world of work, energy, and power. In the last video, we talked about kinetic energy. In this video, topic 3.2, we're going to talk about this concept of work. So this is definitely a word or a concept that you have to be aware that the definition that you use in the real world is going to be a lot different than the definition we use here in physics. So work, okay, is the amount of energy transferred into and out of a system by a force that is exerted on a system over a distance. So the work is going to be done by conservative forces, and we say it's path independent and only depends on the initial and final configurations of that system. And the way we look at this, eventually we're going to talk about potential energy. Potential energy is some of these forces that are, the energy is associated with conservative forces. If you have work done by a non-conservative force, that it'll be path dependent, so it matters how it gets there. Some of the examples of non-conservative forces are going to be friction and air resistance. Conservative forces are forces that conserve energy or momentum, and for us, those are going to be the rest of those forces besides friction and air resistance. Now remember, we talk about energy being a scalar quantity. Work is a concept associated with energy, and it is a scalar quantity also. But you're going to have three scenarios. It's either going to be positive, negative, or zero. And so, again, we're not talking about the direction that it's traveling in. We're just talking about, do we gain energy or do we lose energy? The amount of work done on a system by a constant force will be related to two things. The amount of force that's given, as well as how far it travels. So only components of the force that are parallel. So if you look at this picture over here, she is doing work because she is pushing in the direction, right, with a force, but the displacement of the sled is also in the same direction. So this is what we say by parallel. Those two have to be both either horizontal or vertical. If she was pushing or trying to pull this up while she moved to the right, this would cause, right, no work. So this would be work equals zero. Now, friction will do negative work. Air resistance would do negative work. And so just remember, if it's perpendicular, there is no work being done. So this is where you get these questions about, is there work being done? And they talk about someone carrying a backpack, carrying a tray. As long as they're not moving in the vertical direction, they are doing no work on the tray or the backpack because their displacement and their force do not match up. We can quantify work. So work is going to be equal to F delta X cosine theta. So that cosine theta brings it back to the parallel component and not the perpendicular component. Now, it is also related to energy in something known as the work energy theorem. And this just states that the amount of work done, or the sum of the work done by all the forces, is going to be equal to the change in the kinetic energy of an object. Right? It's not equal to the kinetic energy, but it's equal to the change in energy. All right, so there's the mathematical representation. Work is equal to delta K. Sometimes you'll also see that delta K just simply as delta E, because work changes any energy. But here in AP Physics 1, our main focus is going to be on the kinetic energy. Now, this is where we get a little bit of preview of Physics C. So the amount of work done is going to be equal to the area under the curve of a force versus displacement graph. And so if I want to find the total work done, I have a trapezoid, or I have a square and a triangle. And so I just simply find the area of the rectangle, area of the triangle, add them together. And that gives me the amount of work done. But then I can also go figure out, like, if this started from rest, how fast was it moving after? Or how far did it travel, right? And so you can get different types of questions just based on the graph. All right, so let's do an example problem. So you got a bullet mass, 40 grains, which is about 2.60 times grams, a muzzle velocity of 1,100 feet per second, which is 335 meters per second. Can penetrate 8 1-inch pine boards, each with a thickness of 0.75 inches. I know it's weird that it says 1-inch pine boards, but when we say the thickness is 0.75, that's how boards work. If you get a 2x4, you're really getting a 1 3/4 by 3 3/4 board. Now, what is the average stopping force exerted by the wood? Okay, so you can tackle this a couple ways, but the main thing is you got to come back to the work energy theorem. Okay, where we're looking, the answer is going to be contained here in the work equation. And so what we want to do is you can find the kinetic energy, change in kinetic energy, and then substitute in, or you can just work this all as one problem. Let's say we want to do the change in kinetic energy, right? It's going to be our final minus our initial. Well, our final is going to be 0. And so our change in kinetic energy is going to be -1/2 mv0 squared. Okay, but what you need to do is make sure you convert this to kilograms. Okay, so it's going to be 2.60 times 10 to the -3 kilograms. And so my delta K is going to be -1/2 mass, so 2.60 times 10 to the -3 kilograms times 335 squared. I did this the other way, so I'm going to do the quick calculation. Sometimes it is easier to split these questions up. So that's 146 joules or -146 joules. Remember, energy is a scalar quantity, but if the bullet is losing, right, coming to a stop, it's going to lose energy. Hence the reason why our answer here is negative. And now we just simply plug that into work equals F delta X cosine theta. Well, the cosine theta is going to be 1 because the bullet is traveling this way, the force is exerted this way. They are both horizontal components, so therefore they are perpendicular to each other. Okay, and so we're going to just solve work equals F delta X, and we want to know what is F, so it's going to be W over delta X. But remember, by work energy theorem, we know that the amount of work taken away is -146 joules. Now we have to deal with this 0.75 inches. So 0.75 inches is 0. I wrote this down. 0.01905, but we have 8 of those. And so the thickness or the distance it's traveling is 0.1524 meters. So we put that on the bottom. And we get an answer of -960 newtons. Sorry, I almost forgot what the unit for force was. So that is the amount of force that these pine boards are exerting on the bullet for it to come to a stop. Okay, so now basically the way this unit is set up is you got work energy theorem, and then you work your way into conservation energy, and then finally you adjust power. So in the next video on topic 3.3, we're going to start talking about conservation energy by first focusing on potential energy.